Combining the influences of the three orbital factors of obliquity, eccentricity, and precession, one can reconstruct a history of solar insolation, the amount of solar energy reaching Earth per unit area. Solar insolation oscillates with the periods of its components: 41,000 years obliquity, 100,000 years eccentricity, and 21,000 years precession. At the beginning of the 20th century, estimates of these periods and those of Earth's glacial cycles became sufficiently accurate to suggest a causal relationship between Earth radiation balance and climate. Solar insolation in the northern hemisphere has a greater effect than that of the southern hemisphere, because the northern hemisphere currently has about 65% of Earth's land mass, and land absorbs much more solar energy than oceans. Therefore, when the northern hemisphere receives more solar energy, so does the planet as a whole. The Serbian astrophysicist Milutin Milankovic, 1879 through 1958, proposed that when the solar insolation in the northern hemisphere was relatively high during the December-January period and relatively low during the June-July period, more snow accumulated during the winter and less melted during the summer, causing glaciers to advance and an ice age to occur. How well does this theory fit the observed climatic variations? The delta 18 oxygen of sea bottom sediment cores, a temperature proxy, oscillates with periodicity that reflects changes in obliquity and eccentricities. The influence of precession on delta 18 oxygen is less evident. Changing the alignment between the sun's rotational axis and the gravitational center of the solar system produces intense fluctuations in vertical magnetic fields of the sun. These divert heat flow from deeper layers in the sun and generate patches of fluctuating temperatures on the surface that manifest as sunspots. Although Chinese astronomers recorded the presence of sunspots as early as 28 BC, systematic counts of sunspots began with the invention of the optical telescope. These show that the number of sunspots varies with about an 11-year period, as well as with some less predictable longer cycles. Measurements from spacecraft since 1978 affirm that total solar energy oscillates with 0.05% to 0.07% in synchrony with sunspot number. Variation in solar energy of this magnitude should account for only about a 0.03 degrees Celsius change in global temperatures. Nonetheless, sunspot number and mean surface temperatures of the terrestrial northern hemisphere are positively correlated. For example, the period from 1645 to 1715, the middle of the Little Ice Age, when Europe, North America, perhaps much of the world suffered bitterly cold winters, was largely devoid of sunspots. Do sunspots significantly affect Earth's climate, and might they be responsible for some of the recent climate anomalies? The current consensus is that the influence of sunspots is far smaller than that of many other forcing factors, such as Earth's atmospheric composition. This segment has focused on external forcing factors. Its major points were: number 1, external forcing factors include galactic variations, solar orbital variations, and sunspots. Number 2, galactic variations occur over hundreds of millions of years, and thus are uncertain. Sunlight impinging on Earth depends on the cosine law, Kepler's second law, and inverse square law. Sunlight varies with obliquity, eccentricity, and precession of the solar orbit. Number 5, solar orbital variations may explain glacial and interglacial periods. Lastly, number 6, sunspots have a surprisingly strong influence on climate.